Okay, so let's get started. So what we were doing last time was discussing Kripke structures as label transition systems, and yes, and how labels are actually used, what purpose labels serve. They give a way of specifying, formalizing specifications, and that I was introducing. For that, I mean, specifications are defined as some things that to express constraints on permissible behavior and behaviors that are not permissible. In order to, before doing that, we have to define what what a behavior of system is. So let's take this example. Now, I mean, example of a piece of code, sequential code. When you want to specify a sequential code, okay, the sequential code and any specification tells you what it's considered a specification if it specifies the expected behavior before that, and there are various ways of doing it depending upon what behavior you want to capture or the thing. So I'll ask you a question. So given a program, a sequential code, how would you specify? Suppose you had a factorial program. You were to specify, give a specification for it. How would you specify? Someone?
We would keep track of the variable concerned, n.
What would be I'll be more specific. What would be a desirable specification of a program that computes factorial of its input n?
So if the program in question is an iterative loop.
No, I don't want. Okay, so regardless of what, of course, factorial will require a loop or a recursion or something. Suppose as a black box, I want to specify the desired expected behavior of a box that is supposed to compute factorial. There's an input and it produces an output, which is factorial.
Given an input n, it should produce the output n times n minus 1 time.
Say that again.
So it's just a definition of factorial. Given an input n. Yeah.
So given an input n, its output, when it prints out its output, it has to be factorial n. So that is what is So it's called the input-output behavior. Okay. So you could have, as long as n is C, that may not be a complete specification because maybe there are certain assumptions that the program makes about its inputs. Okay. So given that n is non-negative, then your output will be, if you supply it with inputs that are not negative, which is like under certain conditions of the inputs, you're guaranteed to produce, when I say the output, I mean, you're guaranteed to produce at the output the factorial of n, where factorial is mathematically defined. So it is not supposed to produce its correct input for outside of the input assumption. So if you give the program a negative input, there's no guarantee what the program is supposed to do. Okay, so that is one way. That is called input-output specification. You have constraints of the input and expected constraints on your output, given that your input satisfies. So in other words, your specification is almost like saying for all inputs n, for all n, such that n satisfies your input constraint, for example, n is non-negative, then your output will be whatever factorial applied to n, factorial of n. That is input-output behavior, okay? Now, sometimes that is one way of specifying. So I'm only interested in, what the output is when the program, if the program terminates and so on. But there are other ways of doing it. You can capture the traces that it produces. That's more detailed. So you could say, I mean, if it's a while loop, someone started saying the while loop. Usually you have while loop recursion. Then you could define your behavior as in terms of traces or in terms of execution sequences, where every transition of the program state is captured. In which case, you may be able to express even conditions like whether it terminates or not. Okay, so that is a more detailed behavior, and you can express your constraints on that behavior sometimes. So, for example, here, if there are programs, you allow programs to be non-terminating, like in this case here, a pure input-output behavior cannot even capture the input-output way of specifying. It may not even capture this because this never terminates and gets out of the loop. Then so if you want to allow for non-terminating systems as well, which we want to analyze, because a lot of these embedded systems that we talk about, they don't need to terminate. Okay, because as long as the environment keeps changing, the system responds and it keeps changing. Okay, and so it is the evolution of the state, how the state evolves over time in response to your inputs, the environment that you want to capture. So that's why we define the behavior in terms of execution sequences, possibly infinite execution sequences, and then we use this notion of use traces to capture what the expected behavior is. Okay, so that's why, and that's what I'm trying to motivate, and especially if you have concurrent programs, or various things, like in general, embedded systems are all non-terminating programs. Okay, but that's why we have carefully defined the transition system formalism such that it can also capture, and we use this convention, okay, that I mentioned in the last class, about how you capture even terminating systems, okay, as something which after terminating keeps looping in the same state. Okay, so given that, so we are using this labeled Kripke structures which have a labeling function to define various concepts, especially the behaviors. Okay, so let me go to so that's how we started. Okay, yeah, and we will define two kinds of executions, and correspondingly there'll be behaviors. One is where you can define the behavior of a program as the set of all linear executions, set of all sequences of this kind, starting from any one of the initial states. Okay, and then you can talk about what that set, what the what that set should be as captured in terms of specification. Okay, and this way of doing it also subsumes or includes the input-output behavior. Okay, so if there is a final state after which it'll keep repeating, in that state, the factorial has to be what it is expected to be. If the factorial program never terminates, you will never reach a state, okay, in which it will repeat in which the output is factorial and it stays that way. So you see, so by defining things as set of execution sequences on which you define properties, you can capture non-terminating systems as well. Of course, there are other ways to define behaviors. So this is one way. This is called linear behavior, and there is branching time behavior, in which you capture the actual, if there are multiple, especially if there are multiple successor states, then you can define it as behavior as a tree, evolving trees in which there are several paths leading from the initial state. Now, a trace is, as I said, is a labeled execution of TS that is induced by the labeling function. And the labeling function itself captures certain aspects of the state that we are interested in. Okay? And this labeling function defines the things that you want to do. It's a set of finite propositions. So the behavior of a transfer system is then defined as a set of all traces originating from all initial states, and that's where I want to do use this example, and I will go through this example again. So there is a mistake in here. So my initial state can be any state. It should be x less than or no, it should be y less than or equal to 1 and x is equal to 0. Okay, please make that correction in your mind. X is equal to 0 and y less than or equal to 1, and that's what is captured here. More interestingly, I want to show this because there are some I don't know if there are some mistakes here. So we start with, so when you traces, they require these propositions. Okay, the labeling function associates with every state a proposition which is considered to be true in that state. In our case, let's suppose that we are interested in tracking if x is less than 3 or y is equal to 1. Then, as I said, the labeling function assigns this proposition and its negation. If it tracks the proposition and its negation. So the possible labels for each of the state is these four possibilities. Okay, which is the power set of AP. So the actual executions, linear executions for this example, and the corresponding traces that are induced are shown here. That's what I've shown here as well. When here I'm kind of using the notation when I don't show some, I'm not showing label completely. If there is something missing here, that it means that it can be, So here I'm making it, complete. Okay. So you can have 0, 0 actually is a state when x is less than 3 and y equal to 1 is not true. That is, y is not equal to 1. Okay, and the initial state, there are two possible initial states: one in which x is less than 3 and y is equal to 1, and one in which y is not equal to 1. And this is one way it can evolve, and this is another way that it can evolve. So the actual linear traces, linear executions, and the corresponding traces are what is shown here. Okay. And so what can be your specification? The specification can be, captures some constraints on these traces. Okay. And, so for example, I might want to say that any permissible behavior of this system should be such that every trace should be such that that x is less than 3 should be true in true of every state in the execution, which is captured by this this set of conditions that it imposes on the trace. So that includes, so then if that is the specification, just specifies, we can consider specification as specifying constraints over these over these traces. And you see how the role of label in your specification becomes clear this way. So then your question of whether a system satisfies a specification will be one of showing that the actual traces produced by your system, okay, is included, does not violate this specification, okay? So, yeah, so in this case, that happens to be true. So this is one specification. So every trace, actual trace that is produced by the system, as you know, is such that x is less than or equal to 3 is forever true in all the states, correct? You agree?
Yes, sir.
Yes.
Yeah. But of course, the linear behavior. So that's why the model checking formally, the model checking problem is one of showing that your actual set of the actual behavior, which in this case set of traces produced by the system, is included in the specification. Okay, that it implies the specification. Of course, there are traces which do not belong to the actual traces produced. I mean, executions. I'm sorry. There are executions which are not in the actual behavior, which also happen to satisfy the specification. Can you think of a trace that is not included, that is not a legal execution of this of the system that still satisfies the specification?
Yeah, from the initial state, it can go to x is equal to 1, y is equal to 1. It's not possible to go to that state, but still that trace will satisfy.
Yeah, look at, yeah, I mean, that is, can you be more specific? See, for example, here, there are traces. I mean, there are executions that are not legal executions. We are only considering executions that start from an initial state. But as a specification just says, okay, it can be any trace. Now, I mean, there are execution sequences starting from 2, 3, for example, okay, which is not exactly a legal execution, correct? As per our definition of an execution, is all those sequences of states that start from a legal initial state, okay? So, but I can have execution sequences which start from 2, 3, which is not exactly an legal execution sequence. But the trace induced by that infeasible execution sequence also satisfies the specification, correct? I'm sorry, not from 2, 3, but rather, oh no, no. That is not true. Okay, because no, it is true. X less than 3 is satisfied by execution sequences, the traces starting from 1, 2 as well, correct? Because 1, 2 goes to 2, 3, and 0, 1, and so on. Okay, but that is not a legal execution sequence. As you see, specification is more permissive. Okay, but this specification, I mean, can you name any traces or execution sequences of the system, legal or infeasible execution sequences, that I just showed you an execution sequence, which is not a legal execution sequence, which satisfies the specification as well, like things starting from 2, 3, or 1, 2. Do you agree?
Yes.
Yeah. So, yes.
So the system will check for every possible trace, even invalid ones.
No. that I've defined. As we will see here, I'm introducing all these concepts informally for you to understand. So we will make it very formal. Okay. So as I just now defined, the satisfaction. First, you have to understand what the legal execution sequences are. Okay. That is things starting from initial state. Okay. And a behavior, and actually the behavior of a system also includes only those executions that are starting from any one of the initial states. Therefore, an execution sequence that starts from 2, 3 is not a legal execution sequence because it does not start with an initial state. Okay. Now, what I've not shown in this transition system are things like where x is greater than or equal to 3. But they're also states, right? They're also states in your space, okay? And the transition relation is defined on them as well. So you can you can potentially have an execution sequence, defined by the transition system, which starts from 4, where x is greater than 3, say 3, 1 or 3, 0, something like that. So remember that the transition relation is total. Therefore, you can have execution sequences starting from states in which the label is not of x less than 3. Okay. Now, yeah, correct. Okay, that's so I want you to make the distinction. Okay, so yes, your question was those are not legal execution sequences, so they're not even part of the behavior. Okay, so you're right that we are only interested when you say what it means for a system to satisfy a specification. We're only the goal is to check if the legal behavior, actual legal behavior, is a subset of the specification that is included in the specification. So a specification can be more can be more permissive. Okay, it may also allow certain things. So what we are interested in checking is that our legal behavior, actual behavior, is and the behavior is a subset of this. So if those infeasible traces, for example, starting with where y might be 1, but x is greater than or equal to 3, obviously it does not satisfy this this specification. Okay, the first specification where I insist that the traces should be such that in every state that should include the label x must be less than 3. Okay, but that is true for all legal behaviors. Now, another specification could be which says that eventually the traces should be such that eventually, on every trace there exists a point in time where y becomes 1. Okay. Now y becomes 1. Is that true for this for this system?
Yes.
Correct. No? Although it is not true in initial state. For the second trace, I mean, it is true in initial state itself. If it's obviously true. Eventually true means there exists an I. There exists an I greater than or equal to 0, at which point in the trace that y is equal to 1. The y is equal to 1 is included in the label, which means that y is equal to 1 is true in that state. That is indeed true for both this trace and this trace as well. Okay. As a matter of fact, even every execution sequence is feasible or infeasible of the system satisfies the second specification. Correct? Because even those states, because here I don't even care. You see, I don't care about what x is. I'm only asking the question if y is eventually, if y eventually becomes 1. That is true of not only these feasible executions that start from 2, 3, as well as, infeasible executions, sorry, or even those things that I'm not shown here, where x is greater than or equal to 3. Do you agree?
Yes, sir.
So that is why. So I'm making all these points to kind of informally make you understand these three concepts. Transition system. Given a transition system, it generates a set of legal execution sequences. Okay, and those legal execution sequences induce the behaviors, a set of traces, which is done by using the labeling functions. And the actual behavior of a transition system is defined as in the linear execution as a set of traces. Okay, and a specification is just a constraint on on the set of traces. Okay, and we will see that I've already kind of thrown in this G and F notation, which is actually part of temporal logic. Okay, and they are defined. They actually, semantics is defined such that as capturing some set of labeled traces. Okay, and as you can see, these are sets of things. And if you have an automata that can actually, which accepts these infinite traces, it can also be expressed. Specification can be expressed as an automaton. Yeah. So it's these concepts that I want you to understand. Yeah. And like someone already pointed out, then the task or the formal, the task of model checking is one of showing that the actual behavior, that is the set of traces generated as defined, generated by the transition system, should be a subset, okay, that should be included in the specification, okay, which is also defined as a set of traces. Clear? Any questions? Yeah, I'd like you to respond, at least one of you, if there are no questions, so that I can proceed. Yep, because I can't see your faces.
Okay, I have no questions.
You have one question?
No question.
Oh, okay. So let me. Yeah, or I'll assume. I don't think you need to, I think there is a way to raise your hand in this, no? So I don't know where I will get that, where it shows here. But anyway, this.
Reactions.
Oh, in reactions.
Anyway, if we have a question, we will ask.
That I think so. This is a small class, and therefore, that's not going to be. So let me move on. The branching behavior. So, like I said, the branching behavior, is defined as a set of infinite trees. Okay, starting from a root where its root is one of the initial states, and it captures evolution of the branching behavior as well. From each state, it captures exactly the. The linear behavior also captures all the considered states, but here it precisely captures from each state which is the next state that it goes to. Okay. So and here there are ... Okay, that's why it is branching behavior is defined as a set of infinite trees where the root is any one of the initial states. Okay, so given this transition system shown on the left side as a graph, the branching behavior induced which in actual branching behavior is shown here. Okay, so where this denotes AB, the first component of the the pair denotes the value of AB, and reset, which is the environment, which is the second thing. Okay. Yeah, because this is counting from 0, 0. You know, depending upon what your reset is in the current state, you either go to yeah, you march ahead if the reset is 0, and if the reset is asserted, this is actually false, no? This should be 0, 0. I'm sorry, there is a mistake here as well. Okay, so no. This is okay. This is okay. I'm sorry, because reset is 0 in the initial state, at least in this thing, and that's the assumption that I'm making. In the initial state, reset is 0. So then, since the reset is 0, it will count once, and if in the next state reset is 1, then it gets reset again. Okay, so this is called the branching behavior. Now, when you have a branching behavior, then your specification should also capture, you should be constraints on these kinds of infinite tree. Therefore, you can express these kinds of things. You can say there exists a path from every initial state on which every state satisfies has a certain pattern, kind of a thing. So you can see that intuitively, when you have a branching behavior, you can talk more about, this logic is a bit more expressive, but you will be surprised. Okay, so we will also introduce logics, variants of temporal logic that captures branching behavior. Okay, so corresponding to linear behavior, there is something called linear temporal logic, and corresponding to branching behavior, there is a logic called computational tree logic. All these things are called tree logics, which capture these sets of behaviors of tree. And we will be in the course you will see these two kinds of temporal logics to capture that allow you to express constraints on these kinds of behavior.
Sir, here would there be a different tree with 0, 0, 1 as the initial state? Like
yeah, I mean, if indeed your initial state allows, so here I'm assuming this is the only initial state. Okay, therefore the branching behavior is the initial state is only a single. The set of initial state is a singleton set, and if you allow for reset to be 1, then you will have 0, 0, 1 also a tree, an infinite tree starting from 0, 0, 1 as another permissible execution thing. And yeah, but in this case there is only traces starting 1, 1. From starting initially, because
but in the other figure it's given like 0, 0, 1.
Yeah, you're right. No, but this is a different system, no? What do you mean in the other figure? Which figure?
No, like the
sequential code.
In the left side one, it's given like 0, 0, 1 is also initial, right?
Oh, you're right. You're right.
Reset as 1.
Yeah. So you're right. Good point. I mean that. Yes. I think it should have another trace with 0, 0, 0, 0, 1 as well. Sorry. Yes, because I kind of missed this. So this is not. This is one branching behavior, and then this is one tree, infinite tree in the branching behavior, and there will be another one execution there. Yeah, correct. What are some properties that you can state in this branching behavior? I've already stated one. Like saying on every path originating from every initial, in this thing, in every state satisfies AB less than or equal to 3, correct? So if you label them, so obviously on every path starting from every initial state in this tree, AB is less than or equal to 3. I can ask the question, if I mean, I can pose the specification as asking the question, does, from every, yeah, is it true that from every initial state, there always exists a path in which, okay, is it true that from every initial from every initial state, the branch of behavior, on every path, there it is eventually true that AB is 0?
Yes.
Why?
Because once it hits 1, it will eventually go to 0, assuming reset is 0. If reset is 1, it reaches 0, 0.
Yeah, there's even a simpler answer. Because eventually includes I is equal to 0 state as well. So since the initial state is already the AB is equal to 0, so bang, you don't even have to look at all the states downstream. Okay, but they can be, yeah. So I mean, your answer could have been even simpler, because initial state is one in which AB is already 0. Bang. Okay, eventually the way we will define, you will see, is there exists an I, okay, greater than or equal to 0, such that it is thing. So if something is true in the initial state, eventually is automatically, trivially true. But you will see that here. Then I'll ask the question: if from every if the behavior, okay, such that yeah, what you just now said is it's a bit stronger specification, okay, that 0, 0, AB is equal to 0, 0 happens infinitely often in every branching behavior. What that means is that once not only eventually 0, 0 happens, but once from every state in which is reachable from in which 0, 0 is not true, there is a trace following that in which 0, 0 happens. Like, for example, like you just now explained, I don't know who explained, made that observation. Can you give your name?
Ratnakar.
Ratnakar, okay. So what you were saying was actually true. So infinitely often we see 0, 0 is obviously true in the initial state. Okay, now after that, there are states in which it is not the case that AB is equal to 0, 0. But from that, there always exists. So there exists a state in which 0, 0 is again true. But it's not the case that every path from an initial state that happens to be the case. Okay, because you can have a path in which reset permanently forever is 0. Like where? Here.
Still it will go to 0, 0, right? Because it's a modulo 4 counter.
No. Look at this path, the extreme left path in the tree, in which reset is always 0. So there, it is not the case that you will get 0, 0 infinitely often, correct? Because although it is true in the initial state, that is one path in which you will never get 0, 0. AB will never be 0, 0.
Sir, we're talking about
After 1, 1, it goes to 0.
we're talking about infinite paths, right?
Yeah, no, in paths in your tree. So I'm asking the question: if the behavior satisfies the following condition, that from every initial state, on every path originating from that initial state, is it the case that AB is equal to 0, 0 occurs infinitely often? Okay.
Yes, right. Even in the path that you pointed out, the bottom leftmost one is 0, 0.
Yeah.
Yes.
No, that is actually wrong. Okay. So if it is one, no. You're right. I'm sorry, man. Yeah. Okay, because it's a mod counter, even when it is 0, 0, it is the case. You're right. Okay. Exactly correct. Yeah, because it's counting mod. It happens to be true in this case. Yes. Yeah. Correct. Because it's modulo. Okay. Yeah. So yeah, you could do that. Okay. Obviously, one thing that is not true is because reset is unconstrained by this transition system. This question, this is kind of a trivial thing. So is reset, are there parts in which reset is never asserted? Okay, that is not true. Huh? Correct? It is not true that on every path reset is ever asserted. Okay, because there are that is not true. I'm trying to see if there was something that I can specify which is not true of this behavior. Okay, so you get the picture, huh? So branching behavior is like infinite reset. You can express constraints on these things as well. Yeah. So far, yeah. Question.
This branching behavior or modeling branching behavior only makes sense if our transition system, we want non-determinism to be present, right?
No. See, well, regardless of whether it is there is non-determinism or not, you can still have branching behavior. Oh, but your question is, do we need branching behavior only if yeah, I guess if there is only from every initial state, there is only from every state there is unique next state, then yes, okay. So then yeah, this becomes the two linear behavior and branching behavior will be identical. Okay, it is true. It is true that that is the case. But I think yeah. So in that sense, you need branching behavior will be more significant and interesting if there is multiple next states. Okay, but the reverse question is even more interesting. Was it Ratnakar who made that observation?
Yes.
Yeah. So Ratnakar, you see, the reverse question is, it seems at the outset linear behavior may not be able to capture these branching behavior at all. Okay, is that true? Do you think that is true?
Yes, but I'm assuming the answer is not.
Correct. Okay, because you see, it may intuitively at first outset you will think, linear behavior. If you only consider linear behavior, it's very extremely thing. I mean, if you have multiple next states, how does it even capture? No, that is actually not true, because there are lots of, you can capture branching behaviors also, indirectly as linear behaviors, because it's a set of possible trace, all the traces are set, there is one trace for every next state that is possible there also. Okay. So, so it is not the case that just because you restricted yourself to linear behaviors that you won't be able to capture certain non-deterministic behaviors. That is certainly not true. As a matter of fact, what is even more interesting is, even though you may think that branching behavior will be more strictly more expressive than linear behavior, that is not true. Okay. Actually, there are things that linear behavior can capture that a branching behavior as a specification language will not be able to capture, which is what would be very surprising. Okay, so so you will see that just because you have branching behavior this way, there will be a certain branching temporal logic will not be able to capture. Okay, so at the logic level. But you're right that if you allow for infinite trees, that you have more expressiveness. See, there'll be lots of these kinds of interesting questions. Okay, when you define logics to capture different kinds of behaviors that you can pose. Okay, whether this logic is more expressive than the other one, and so on. So I think there are two observations here. That we got, thanks to Ratnakar's observation, that one is, yes, if there is no non-determinism, the two behaviors are identical, but these logics that describe branching behavior and linear behavior surprisingly can capture certain aspects of branching behavior as well. That is the other thing. And the logic which I have not defined, that the logics that can capture branching behavior and linear behaviors, they are, in terms of expressive power, they can be varying, and we will see that. Okay. Yes. And as we move along, transition system I've formally defined. We will, behaviors I've also actually formally defined as well. What remains is the temporal logics we will have to define, and the actual formalize the problem of model checking as a satisfaction problem. All those things we will do as we move along. Yeah, so far we have just looked at these things. Modeling examples is something that I will get to in the next slide. Modeling transition systems symbolically. We have already seen examples where a transition system relation and the initial state can be modeled symbolically. I know that Ratnakar, you missed that lecture, but we will show that examples in the next thing that I have. Yeah. What file did I want? Okay, before I do that, because I want to introduce you, before I actually show how we can symbolically, when I say symbolically capture something, what I mean is, how do you use appropriate logic, either propositional logic, and now I'll be introducing what is called quantified Boolean formula, and using either propositional logic or quantified a Boolean logic to model transition systems, its behaviors, and also and its behaviors. Okay, either linear or branching. That is one aspect. And then when we introduce temporal logic, you will see how we can express the specification or constraints on these behaviors as formulas in that in that logic. So now I'm going to be introducing quantified Boolean logic and illustrate how I can use quantified Boolean formulas to model transition systems and its behaviors. Okay. Before that, I wanted to make one other observation, so which is related to related to this Kripke structure, okay, and the impact of restricting our labels, the AP, the set AP, to be to contain only a finite number of propositions. See, that has this, of course, I illustrated how labels are important for defining traces, and in terms of which specification is defined. Okay, you understand that, correct?
Yes.
Yeah.
Yes.
Yeah. So there is another impact that it has. The fact that you have only finite propositions. Okay, like I showed here, indirectly it kind of shrinks the states in your system to become finite, isn't it? Because if I have only these two propositions to track, x is less than 3 and y is equal to 1, my states can be actually partitioned into sets, into sets or subsets that satisfy that, in which every state satisfies one of these three finite number of possibilities, right? So although my transition system, the state space of my transition system in here has infinite number of states, correct? Also, yeah.
I have a question here.
Yes, yeah.
2 power AP, you wrote there. Yeah. In that the last clause, not x less than 3, not y is equal to, this will contain infinite number of states.
That's exactly what I'm saying. But it kind of coalesces, no? I'm only, the traces will only have these 4 things. Therefore, you kind of have, say, all the states in which x is greater than or equal to 3, okay? And y can be anything, they're all. So you're right that that's exactly what I'm trying to say, okay? You have the effect of, since you, if you operate in terms of these formulas, okay, or, in terms of these label sets, so you are, coalescing in some sense an infinite number of states into this condition, okay? And therefore you could analyze, these behaviors that, these specifications, the behaviors that we talked about, that we cared about, or whether forever x is less than 3, okay? It is not the case that, it is always the case x is less than 3, okay? So although this is an infinite system, we could pose this and then answer this for this infinite case as well. I'm pointing this thing as an aside, okay? What happens is, by insisting that this labels AP set is only a finite number of propositions, I am restricting my specification to such states in which they are labeled only in a finitely many ways. That's why all these logics that we define will be what are called propositional temporal logic, okay? In the sense, we only have a finite number of propositions, okay? And we only track evolution of the truth value of those finite number of propositions, okay? That inherently allows this kind of introduce this kind of an abstraction. Although, my system is infinite, if I restrict myself, I can coalesce these states into into those in which one of these conditions holds good. Then I can put, okay, I can capture, as a matter of fact, I can have one circle here to capture everything which is in which x is greater than or equal to 3, and maybe y is equal to 0, 1, 2, and a certain finite, and then be able to do, okay, be able to make it into a finite state system, okay? So this is an aside, okay? And for simplicity, we will assume we have finite state systems, but that is a trick that you can actually use. And so it allows you to analyze infinite state systems in which your propositions are only finite, which will effectively mean that you can coalesce some of these states into an infinite number of states into one in which one of these conditions is satisfying, and you can come up with a finite transition system, okay, in which you can get an abstraction of this. Since we're talking about modeling, I can abstract such an infinite state system in which there are infinite number of bubbles into something which contains only a finite number of bubbles. Okay, that is the point I wanted to make. Okay, yeah.
Sir, I wanted to clarify one thing. Are you saying that we can coalesce it into precisely the number of states as 2 power AP?
Correct.
But if that is the case, then we're not able to distinguish between 1 comma 2, like in the diagram here we're not able to distinguish between 1 comma 2 and 2 comma 3, even though we're supposed to be able to, because both of them will fall under x less than 3 but not y equal
Yeah,
to 1.
I mean, you're right. Okay, so I think I need to have, yeah, some things. Okay, I need to extend these labels. Okay, a little bit. You have to be careful about. Yes, that's a good point. You have to be careful about that. So I need to have exactly, maybe in order to distinguish that, I have to extend. I cannot have just y is equal to 1 and not y is equal to 1. I will have to say y is equal to, 1, both in terms of x and 1. I might have to say 1, 2, and 3, okay? And all the rest, okay? I mean, I can choose these labels. Still, I can have finite labels, okay? To do that. What I will not be able to do is, so you're right. In order to distinguish these two things, I'll have to make my labels a little bit more. I mean, I have to use more labels. So that particular thing, I mean, I can do. But what I will not be able to do is, I cannot talk about behaviors in which y can be, I cannot distinguish between y is equal to, given a set of things, you're right, given a set of labels, in this case, it will even coalesce these things, correct, okay? So if I have to distinguish between these two things, in this case, my properties that I can express really don't distinguish between these two things at all, although I've shown that, okay? In the way, because I only can talk about either y is equal to 1 or y is not equal to 1, correct? But yes, but the point I'm making is, once you choose your labels, you can always coalesce it to talk about whatever behavior or properties that you can express using those set of propositions. Yeah, that's what I mean. Does that answer your question?
Actually, do we need to like distinguish between the two states, like 1, 2, and 2, 3? Because the specification is actually based on
indeed, if I only care about x's, whether x is less than 3 and y is equal to 1 or not y is equal to 1, I don't need to. That is exactly what I'm saying. So you can even, given these are the only labels that you care about, I can even abstract this system even further by coalescing these things. Yeah.
Yeah. Yes.
And that's the point I'm making. Yeah. Yeah. So which is what was observed here as well. You can further coalesce in the thing. But if you, yes. So in this case, you can do it. So yes. So once you have these propositions, those are the so many states that you can actually distinguish. Okay. And your actual system, even if you have more number of states, whether it's infinite or not infinite, your actual transition relation, your state variables, etc., you can choose the way you want, you can express it. But once you choose your propositions, then relative to those propositions and what the specification can distinguish, you can actually coalesce states, okay? And then indeed model your thing only using a smaller number of, I mean, those states that your propositions can distinguish. Okay. So if you have a finite number of propositions, then effectively you can abstract away. You can coalesce states into these states. So it effectively you are making a finite state system out of it. Yeah.
Yes, sir.
Yeah. So in that sense, all the behavior, the way I've defined the quickly structured by the fact that I'm restricting myself to finite set of propositions. These are all describing, even if the system is infinite, it is the kind of behaviors with respect to the behavior you are able to express only certain capture certain finite kind of properties. Okay, so that is true of these things, and that's why sometimes, if you're by defining this behavior, you're effectively restricting yourself to analyzing, in some sense, finite state systems. Okay, so to the extent that you can, claim that, oh, I'm analyzing infinite state systems, is what it really means is I'm analyzing finite abstractions induced by these propositions of that infinite state system. Okay, so that is what I'm trying to say. Okay, so I'll introduce quantified Boolean formula, and then I'll get to example where I'll show you how I revisit modeling transition system as using proposition logic and behaviors using QBF. So what is quantified Boolean formula? So here's the syntax. The constants 1 and 0 belong to his okay, there is the proposition part. It includes everything that is included in propositional logic. So a finite number of proposition variables, they all belong to QBF. And there are usual connectives, logical connectives, non-negation, conjunction, disjunction, implication, and so on, the usual Boolean connectives. So that is propositional part, the first 5 bullets or 4 bullets. Okay, now I'm adding quantifiers. Okay, the quantifiers over only propositional variables. Okay, where x belongs to vars. These are propositional variables where x can take. They are propositional variables in the sense that they range over sets which have 1 or 0. Okay. So given that, then for all x, and there exists an x, there exists those are belong to QBF. So example, you can have this is how first order predicate calculus is defined. Okay, except that first order predicate calculus, what is the difference here between first order predicate calculus and the way that I've defined here?
The domain can be any arbitrary set here.
That is one, correct. Yeah, the domain, it's the domain. Okay, yeah. And proposition first order predicate calculus also has terms, functional terms, now, so which I'm not. The only terms are propositional terms. Okay, whereas there you can have functions that is defined over those domains, but here they are just propositional things. So examples, for example, you can nest quantifiers and combine using. So these are some examples of propositional formulas. Okay, so quantified Boolean formulas. This is just a fragment of your full first order predicate calculus, where the variables range over, they are proposition variables, meaning they range over sets that contain 1 and 0. So, and yeah, so just to remind you, W is set to occur free in psi1. Yeah, so once you introduce a quantifier, X is said to be bound in this for all universally quantified formula, and similarly, X is said to be bound in this existentially quantified formula. But anything that is not bound by one of these quantifiers is said to be free in the subformula. And if there are free variables in a formula, then it is said to be an open formula. If every variable that occurs is bound by some quantifier in the formula, then it is called a closed formula, or is sometimes referred to as a sentence. If every variable is bound by some quantifier in that. So here are examples. I have to keep track of time. So we started at 8, 9. Oh, it's almost time, man. So it's 9:15. So I don't want to keep you very late. So I will just introduce informal semantics, and I will get to the thing next. Oh. Chat 3, what is? Okay, good. So we did that. Okay, informal semantics. Okay, so now that you know for all, informal semantics for all, is this formula satisfiable? That's the question that I'm asking.
Yes.
Why?
We can set y to be true.
Yeah. So if it's 1, if X is 1, it is true anyway. If X is 0, so this formula is true if it is true for every possible instantiation of X. So you will have to analyze 0 and 1. So what you said is correct, that you can always choose Y to be 1, okay? So that you can make this formula true regardless of what you instantiate X with, okay? And that's why this is satisfiable, yeah? So by 1, I mean you can make, by making Y to be 1, you can always make this satisfiable. So, but Y is equal to 0 is not a satisfying instance of this, correct?
Yes.
Yeah.
So that's the informal semantics, and that's how we will define the things. How about this?
No. It's
Yeah.
not.
Yeah. So that's one. It is not satisfiable.
Satisfied.
Yeah, obviously, because when for all X is satisfiable, this is 2. I've shown just one instance.
It's also true.
Yeah, so in this case, there is another instance as well. Even when you choose Y to be 0, it is satisfiable. Of course, Y is equal to, if you choose Y is equal to 1, it's also satisfiable, correct? Yeah. So there are more satisfying instances for this formula. How about this?
Yeah, it is satisfied. Y equal to 1.
No, how? You're right. Yeah, Y is equal to 1, correct. Yeah. So because I'm only insisting Y is equal to 1, so there is an X. But you will have to make Y is equal to 1. So I should say this is not too expressive. So yes, by making Y is equal to 1, it is satisfied. Correct. So Y. I've not shown the fact. These instantiations are for the free variables in there. So here is a closed formula.
No, because if we set x and y to 0, it fails.
Yeah.
Oh, sorry. We're asking satisfiability.
No, no. Yeah, I'm asking satisfiability, but it is not. So, so actually, it is not. It is not satisfiable for every x and y. Okay. Wait a minute. Yeah. So it is because it is. See, it's a closed formula. Okay. Therefore, it can only closed formulas. They're either valid or not. So, I mean, the satisfiability of this thing is true because of universal quantifier. It is, I mean, it's true only if it is satisfied, only if it's valid. Okay. So when you have, see, the satisfiability question can be, is there only if there is some free variables. If it's a closed formula, like it is the case here.
Yeah, got it. I made a mistake.
Yeah, so it is either it is satisfiable only if it is satisfiable, it will be valid, okay, or it is not satisfiable. So this one,
True. You set y equal to 1 and that should work.
yeah. No. Yeah, it is true. So if y is equal to, actually for all possibilities, even if x is equal to 1, it is trivially true. If because if you set x is equal to 1, it is trivially true because this reduces to true. There exists a y which is true. Okay. And if x is equal to 0, then you can set y is equal to 1, and therefore it is valid. Okay. So let's look at the consequent here for all x.
That's false.
Now that's false. So the only way that this thing can be,
We can set w to be false and
That's
then a whole
Yeah.
statement.
And
right.
y also should be false.
Yes. Okay. I mean, then w being false, there is always yeah. This has to be. You have to make the antecedent false. Okay. Then this will be true. Therefore, this, for w is equal to 0. Okay. Since w is free, you see. Therefore, the satisfiability question is still alive. Yeah. So as someone pointed out, w is equal to 0 can make it false. It's only yeah. So similarly here, then this question of satisfiability of this reduces to saying if there is a non-satisfying instance of the antecedent. Okay. Now in this case, this is obviously valid because this one is, the antecedent itself is unsatisfiable. Okay, it is unsatisfiable, and therefore it is not valid, and therefore it is false. Completely. So that's why this is happens to be valid. Okay, because this one is, the antecedent is equivalent to false, and therefore this is always a true. Yeah. So, and this is because it's a sentence. A sentence is always either valid or unsatisfiable. And in this case, in the case of the previous example, it happens to be valid. Okay. Yeah, and also satisfiability of an open formula phi can be checked with satisfiability of this sentence. So what I'm saying is the satisfiability of an open formula is equivalent to checking the raising the thing of I mean, checking the validity of the sentence, of the closed formula, okay, of this, if you put in an existential quantification, if that formula is valid, then the original formula phi, in which the variables in X are free, is satisfiable. Okay, so I think I will stop here because it's getting late. Or I mean, am I okay taking 10 minutes?
I think so. Fine.
I need to hear from everybody. Or we
Okay,
can,
for
Yeah, it's okay.
so yeah, so you can, the formal semantics is defined much like thing. One is, here I'm defining satisfiability, whether it is satisfiable at 0 is unsatisfiable, not is satisfiable if only thing, and these things remain the same. And yeah, read this psi as real psi. Okay, there's a mistake in LaTeX that I had. So for all X is satisfiable if and only if yes, psi X bar and psi X are satisfiable, where psi X bar is the result that you get by replacing X by 1. Psi X denotes the formula that you get by replacing X to be 1, and psi X bar is the formula that you get when you replace X to be 0. Okay, so that's how it is recursively defined. So for all X is satisfiable if both instantiations of X is equal to 0 and X is equal to 1 are satisfiable. There exists an X is satisfiable if one of them, one or both are satisfiable, even if one of them is the replacement of X is satisfiable. So the question is, there is a question that must have come to your mind, okay, which is, do you really need a quantified Boolean formula? Does it add anything to your expressive power that proposition logic does not get you?
no, I guess.
Yeah.
In this case, it doesn't feel like that because our domain is restricted to 2 values.
2 values, therefore you can expand it out, okay? So then you can ask the question, why are we even bothered with this?
It's just a syntactic sugar kind of thing.
Yeah, I think there are 2. Yeah, yes, syntactic succinctness. Okay, that is certainly one. Your certain things you can express very compactly. Okay, because here, for all X is, if you expand it out, there is a branching. No, one case for X equal to 0 and the other case for X equal to 0. So there's an exponential, blow up. So you can express things exponentially more compactly if you had quantified formulas. Okay? I mean, if you can use quantifiers. Okay, so it comes in handy to express things in a compact fashion. And if you're able to actually decide the satisfiability without expanding it out, so SAT solvers do correspond to propositional logic, okay, with the quantifiers. But there are extensions to SAT solvers where they decide the satisfiability of quantified Boolean formulas without actually expanding. So in some case, so then if that is, there is obviously the complexity of the satisfiability of quantified Boolean formula is decidable, but it is much harder. It's harder than NP. Okay, it belongs to a complexity class, which is harder than NP. I mean, you can check it out what the thing is, and I think I don't know exactly the complexity class that it belongs to, but yeah, but
I think it's P space.
yeah, you're right. I think model checking is P space as well, and this model checking is.
We had it in our class yesterday, complexity.
Yeah. So it is, whether it's p-space or even hard. I mean, yeah, I think it's p-space. You're right. Okay, because finite state model checking is p-space and it can be expressed. It requires solving quantified. It can be expressed succinctly. The problem itself is quantified as satisfaction of a quantified Boolean formula. Okay, so it is p-space. So and that's p-space still. So it is harder, but if you can solve it in some cases efficiently, then it can be used. So I will just introduce this transition system and stop here. Okay. So consider the transition relation. I've already given you examples of transition systems, and based on what I've introduced today here, you can actually, as exercises, try and model what I'm doing here for this transition system, for those examples, the code example and the hardware example that I have already shown you. So I'm, considering the system in which the transition relation is defined. This one corresponds to a system which really shifts. It has 2 bits as its state component. And when I say input, you really mean the state. Okay, they're not like input, but there are two state bits are there, and the transition system really corresponds to shifting the bits in the state to the right and moving 0, bringing in 0 in on the left side. Okay, that's what this thing says, because here the transition relation, as you know, relates the current state with the successor state. So x1, x0 is the current state, y1, y0 is the next state. Okay, the bits in the next state. So I'm defining y0 to be identical to x1. Okay, so it is so that's why I'm saying that it is being shifted to the right. And y1, the most significant bit in the next state, is 0. So 0 is always being moved in. So what are the satisfiable instances of this? That is the model of this formula. And what does it informally represent?
X0 should be 1, right? So
Right.
X1 can be 1 over 0.
Right.
Then, so y1, y0, like y0 will be y0 is y0 can be 1 or 0. Right?
Yeah. So one way is to express it things. So it is. So exactly right. So it is. It captures all the successor states of all starting states in which the least significant bit is 1 under this transition relation. That's what it captures. Okay. It captures the set of all successor states under the transition relation, which the starting state is such that its least significant bit is 1. Okay, so read this as, okay, 0, 1, 1, 1, 1. Okay, those are the two. So that's the start state, and this is the next state. Okay, got it?
Yes.
Yeah. So informally, if you, what I said in English, okay? So it is kind of the image of the set of states in which the least significant image under the transitive relation T of the set of states in which the least significant bit is 1. That's what it captures. So in other words, this is a symbolic representation of that set of all successor states of those states in which those starting states in which the least significant bit is 1. Okay. You should get an idea. So where I'm headed. Okay. So this is how. So by you can manipulate these, use formulas to represent set of states, and therefore you can even behaviors can be represented as formulas. Okay. So similarly, you can, you can even use the Boolean formula. So there exists an x0, x1, x0 such that this is true. So first of all, this predicate, this is a formula, and a formula denotes a predicate. Okay. And so this formula has y1, y0 to be free. So when I say what does this denote, what does that mean? What a formula denotes is the set of satisfying instances, correct? Okay, that's how you should understand it when I ask this question. What does it denote means? What are the set of satisfying instances of this formula? So it is the image of it is the image of this set, okay, in which the least significant bit is 1. Okay, so here this is a formula over several variables. Now this one is now a formula over just y1 and y0. Okay, so by using existential quantification, so this is the image of this set under T. Okay, one in which what I was originally talking about. So if it is in it, so I'm just here, I'm considering just the image of this particular image of the set 0, 1, 1, 1 under T. Yeah, I think it's a bit, I don't know if it's, you understand this and where it's a bit too late in the thing. So do you agree?
Yes, I think there was a little confusion because it wasn't clear what was the input, what was the output.
Yeah. I mean, the other two people, you have to be vocal as well. Amin and
yes, yes.
Yeah,
Got the question.
Yeah, the distinction here is by existentially quantifying this one, I'm making this formula over just the post variables, okay? Under this constraint. So it gives all the successor states of those under T, success states of the starting states in which the least significant bit is 1, which is also the case here. It's just that here the thing is you have to have x1, x0 also. Okay, so here because I'm existentially quantifying out this input thing, it just gives 0, 0 and 0, 1, which is the successor states of these things. So You see, so you can express images under T, pre-images, etc., using quantified Boolean formula. Okay. Now you can expand this thing out. So okay, so one more example that I will show. What does this denote?
One zero and 1 1.
Yeah, but
0 1 and 0 0.
yeah, but give me an intuitive explanation. Okay. It gives set of all inputs, which means set of all initial states. You're right. I don't know who said 0 0 0 1, but that is correct. It gives intuitively what it means is set of all initial states that get mapped to an output whose least significant bit is 1 in the next state. Okay. It's a pre-image under T of states in which the least significant bit is 0. So 0 0 least gets yeah. See, from 0 0, the next state will satisfy. The least significant will be 0 because it is shifted, right? So is the case for this 0 1. So it's a set of all initial states. By inputs, I mean starting states that get mapped to an output state whose least significant bit is 1. Okay. So that's why I call this as a pre-image. This is a post-image of a given set. This is the post-image of a given set. This is a pre-image of a set with certain constraint. Okay, it is a set of all starting states which get mapped to some state in which the least significant bit is 0 in the post state. Okay. Yeah.
Like, shouldn't it be least significant bit is 0?
Yeah, that's, yeah. Did I say 1? The least significant bit is 0.
It's written here as 1. It get mapped to an output whose least significant
you're right.
is
You're right.
1.
This is wrong. Okay. The least significant, whose least significant, it is the set of all inputs that get mapped to an output whose should be 0. Correct, man. Yeah, I will make that correction. Yes. Whose least significant bit is 0 because I'm constrained.
Not of y0 is given.
Yeah, not of y0 is true. Yeah, what does this denote? Yeah, I'm not constraining the output at all. Okay, so it is just all successive states under T from a arbitrary input. Okay, by arbitrary input, initial state could be anything. Okay, so this gives you the set of all successive states under T starting from an arbitrary state. Okay, by input I mean initial start state. So this captures the image under T of any arbitrary state. So input could be either 0 0, 0 1. No, that's
Input can be anything, right? And like,
correct.
Because y1 should always be 0. So like in the output, only 2 outputs are there, 0 0 0.
That's right. So the y1, this is wrong, isn't it? But you get the idea. So there exists an x1 x0 such that t holds good. So if it is 0, no, I think this is not. If it is 0, 0, the output will be 0, 0. If it is 0, 1, it will be 0, 0. Correct. If it will be 1, 0, it will be 0, 0. If it is 1, 1, it will be 0, 1. Okay. So this is correct. Okay. So yeah. So see, if the initial state, if the start state is 0, 0, then your output will be 0, 0. The start state is 1, 0. Your next state will be 0, 1. If it is 1, 1 also, that gets mapped to 0, 1. If it is 1, 0, it gets mapped to 0, 0. Okay. So that's why I say it's all success states under T from an on arbitrary initial set of states. Yeah. So you see, I mean, that's why you will see that we will use quantified Boolean formulas in our thing, regardless of whether you will expand it out or not. So because an equisatisfiable unquantified version of the formula is this one, and so it is compact to talk about those things. So I think that's the point, and I'll stop here. Yeah. Unless you have questions. Yeah, I would study these slides and also try, those examples that you capture to express one-step image and so on. You have to become familiar and completely at ease with using these QBF to model things. Yeah. So I urge you to review these slides and then work out some examples, even on this thing or the other examples that I've given you as exercises, for you to do. Yeah. So do you have any questions? I'll stop sharing.
Sir, I wasn't present when you told us, but what are the guidelines for accessing that MIT Press?
Just one moment. Yeah. Just one moment. Stop sharing. Say that again. So.
What are the guidelines for accessing the textbook? Like, are we all allowed to access it? I wasn't there when you told us. The MIT Press username, password, the reference for the course.
Oh, the reference textbook.
Yeah. Yeah,
I published it, no?
No. I didn't know whether or not we're supposed to access it or not.
Yeah. It's for that reason only. Yeah, you're more than welcome. I think what I will do is from the one in the lectures, I will give the appropriate chapters. Okay, before the lectures. The thing I think I follow the chapters in that book fairly closely. Yeah, you can.
Okay.
I uploaded it. It is meant for you to access using that login ID and so on. So there's only one user who can use it at a time. So you will have to coordinate amongst you. Okay, if somebody else is using, you just need to send an email saying, okay, when you will be done, so I can use it. Yeah.
If we find the name, I think we can get a soft copy among ourselves.
If you find the name means?
Yeah, I think it's there in Moodle, the name.
Yeah, it's there in Moodle. The login ID and password is there on Moodle page.
So he's asking for the book name, I guess.
Oh, for the so you would try to get your own version, your own copy.
Yes.
Well, then you have to go to MIT Press. You have to pay for it. It's not free.
I meant through other sources.
No, I don't think you have. How can you get it? No, there is no PDF version. Firstly, it's not even legal to do that. No, I mean, I know, I've done it too. So I couldn't get a PDF version here. Okay.
What's
Some
the
PDF,
what's
some
the-
PDF versions are available. Okay, so that is the, I've already uploaded the introduction set of slides. There is the cover for the book. So you could try to see if you can get
Yeah,
a
we'll-
PDF somehow. Then you're welcome to do. So welcome to use it. So I subscribed via CMI once for this, and that's why I'm letting you share. I'm letting you access that. I'm sharing that with you. But if you want to get your own PDF version, so there are 2 copies in the library, but that is not much used now in these COVID times, is it? So I think there are 2 copies of this book in the library. But since you cannot access it, there are only 2 ways. Either you type share the ebook edition, or you find some locate a PDF on the net yourself. Yeah.
Yeah, thanks.
Okay, I'm going to, if there are no further questions, I'll end. Oh, by the way, what do you want to do starting Friday? I mean, is this time you prefer, or you prefer to move it to some morning time?
The current time itself is okay for me.
I want to hear from all 3 of you. Okay, so give your name and then you think. Is it okay with all 3 of you?
Yeah, for me it's okay. This is Amin.
Amin, okay.
Yeah,
How
I'm also okay, Padamalai.
about Ratnakar?
I'm also fine with it.
Okay,
Yeah.
so then we can continue unless I feel like I need to do. So I might, yeah, I'll also see, scheduling in the morning is probably needs a little bit coordination. Okay, but it's not doable. So I might want to free myself, okay, with my family for this. So I will choose. So for Friday, let's continue with this, okay? And then I will decide also, okay? And if I feel like I want to move it in the morning, what would be a good time to move it in the morning based on your other courses that you're taking?
I am free on Friday anytime.
Every day, every course I am attending starts after 12.
I think this will need even for 3 people some email exchanges, or I can do Doodle. Okay, so there is something called
We'll
Doodle.
talk among ourselves and discuss.
Yeah. So give me a few options here. Discuss among yourself and give me two. I mean, yeah, this is the only course I'm teaching, so any time should be okay with me. Okay, so in the morning or afternoon, any slot. So yeah, that's the best. Okay, you discuss amongst yourself and let me know. Yep.
You specifically want a morning slot.
Is it okay with?
Well, afternoon is also okay. 3:30 to
Yes.
5 is also okay. So preferably before 5. Yeah.
Okay,
Yeah,
we'll
we'll
discuss among
discuss.
ourselves and let you know.
Okay. Sure. Thank you. Bye.
Bye, sir.